Okay, so we continue with our journey of bifurcations. And today we are going to study a different kind of bifurcations. Bifurcations not from fixed points but cycles. So, so let's say what is the global versus local bifurcations. So local bifurcations they occur in the neighborhood of a single fixed point. However, global bifurcations involve large regions of the phase space. Typically, they are the bifurcations of cycle. Remember, we saw glimpses of it in the last lecture where the attracting and the repelling limit cycle collided together and annihilated each other. So, let's see what these global bifurcations are. So, the first one is very analogous to the fixed point bifurcations. We have something called as the saddle node bifurcation of cycles. So this is typically when a bifurcation, when two limit cycles join or coalesce and annihilate each other. That's the saddle node bifurcation of cycles. So remember example from our previous lesson, we have this dynamical system and theta dot cos. And as we saw in the last lecture, if I draw this dynamical system, this is R, this is my mu less than 0. We were interested in mu greater than 0 and how there was a bifurcation starting at this point, minus 1 by 4. I had two limit cycles. One was the attraction limit cycle and the other one continued here, and the focus there was the bifurcation over here where the fixed point at r equals to 0 loses its stability and the only other attractor in town was the stable limit cycle, so there was a jump to the stable attractor. Here we are considering the journey of the fixed point at mu, the critical value mu minus 1 by 4, how this unstable attractor limit cycle and the stable limit cycle coalesce over here and destroy each other here at this particular point. So this is the focus of this chapter. And this is the annihilation of two limit cycles, and that's why it's called as at this bifurcation point. So that's why it's the bifurcation in which two limit cycles coalesce and annihilate each other. So the other way of examining the same system is through your usual phase diagram. Namely, I have this time R dot and R. So I'm primarily right now interested in, so this was my dynamical system. And I just bring it here again. Over here. So let's say what's going on. So I'm just focusing on this 1D system for now over here, and I know this point is interesting, so this is, I can call it as a mu critical equals to minus 1 by 4. So at the critical point or less than the critical point, this curve looks like something like over here, and you know that r equals to 0 was a stable fixed point, and in the picture of theta and phi, this is what an actual picture, this is what's happening. Now remember, as I crank up mu, this hill is going to collide with this axis, and I'll immediately get two more fixed points. So that's essentially what's happening, and you can look at it in terms of the system. I had r dot as mu r plus r cube minus r5, and if I solve for the roots, I have r when I demand mu plus r square minus r4. We did this in the last lecture, 0, and that gave me either r equals to 0 or I had r square plus minus as half plus minus 1 plus 4 mu upon 2, and that you can see y mu less than minus 1 by 4, I have no fixed points. These fixed points are going to be born as this hill goes up in this direction. So at mu equals to mu c, the critical value, I essentially get exactly for this one-dimensional system the saddle node bifurcation. I get this hill now touches the surface, and I get a half stable, half unstable node, half stable, half unstable fixed point. And what does that look in the picture now? Well, I have a half stable limit cycle, and I have a stable fixed point because all trajectories here go here. So I have this guy, all these trajectories going inside, and this limit cycle is half stable, meaning all trajectories outside over here, arrow, they get attracted to this limit cycle. So this is the half stable, half unstable limit cycle. And remember, in the bifurcation diagram here, we are on this point 1. And as I increase mu beyond the critical value minus 1 by 4, I have this one half stable, half unstable limit cycle in 2 dimension, or half stable, half unstable fixed point in 1 dimension splits into 2. I got an unstable limit cycle and I have got a stable limit cycle. And that's in the bifurcation diagram also, or in the, you can see it over here, R dot R over here. So I have here, and this was my unstable point. So this is for mu, which is greater than the critical value, but still less than 0. And this was basically my figure where I had a stable fixed point, I had an unstable limit cycle, and I had a stable limit cycle. So this corresponded to this guy, this corresponded to this guy, and of course I had this as my stable point over here. So that essentially and if you can notice, at the birth, at this position, my limit cycle had this much amplitude, which is roughly order of 1, and that is the critical point of that distinguishes it from a supercritical Hopf bifurcation. So at the birth, at the cycle has oscillations of order 1 magnitude in contrast to a usual supercritical Hopf bifurcation, where the limit cycle we saw has a small amplitude which roughly scales as this guy. So once again, if you look at in 1 dimension, this is just your usual saddle node bifurcation. This is our saddle node bifurcation in 2D. This is the saddle node bifurcation of cycles. I track it backwards, so if I crank up the parameter less, so I'm going to go up, these cycles are going to come and they are going to vanish. So basically in this figure, two cycles combine and at this point, beyond this point, destroy each other. Two cycles coalesce and annihilate as mu goes less than mu c. Okay, so this was the saddle node bifurcations or cycles in pretty much a similar analog as the saddle node bifurcation of fixed points. Let's see one more example of global bifurcation of cycles. So we are going to study the infinite period bifurcations. So till now we were concerned mainly, one of the things we remember, we keep saying about this amplitude, and roughly the underlying assumption was that the time period of the cycle was of the order 1 only. This guy to rotate around the cycle took the time which was roughly, it didn't even come under some sort of a discussion, whereas we were interested in the magnitude of the cycles for Hopf bifurcation, supercritical bifurcations. But there can be a dynamical system in which the behavior is changing not in space, but the behavior can actually change in time also. So let's look at that. So I have a dynamical system. So if you can look at it right off the bat, these are two one-dimensional systems. I can just treat them independently. I have r dot equals to r1 minus r square, and I have r equals to 0 as unstable fixed point, r equals to 1 as a stable fixed point. Therefore, all trajectories approach the unit circle monotonically. You can also see this in the bifurcation. This is r dot, and this is the kind of the map we have. This was the stable fixed point, and this was the unstable fixed point, just like the things we have been doing. So what happens in the angular? So this is what's happening in the radial direction. In the angular direction, let me write down. if I have for mu greater than 1, this guy is always positive and my entire motion is in the counterclockwise direction. So I have this guy is the fixed point, and all the trajectories spiral to r equals to 1 in the counterclockwise direction. And I can also say theta dot decides the angular velocity. So if I measure my theta this way, this guy is going to be, theta dot is going to be mu minus sine theta. Sine theta at pi by 2 is 1. So this is going to be very slow. And over here, sine theta for 3 pi by 2 is going to be minus 1. So that's going to be mu plus 1. So that's going to be, so over here theta dot is mu plus 1. Over here theta dot was mu minus 1. I'm assuming mu is positive. This is going to be fast. That's essentially what's happening. The trajectory is going to go on the attractor, but over here in the angular sectors, the trajectory is going to be fast, and over here it's going to slow down a lot. And this is specifically true. So what actually happens at mu equals to 1? Look, at mu equals to 1, theta dot would be 1 minus sine theta. And when sine theta is positive, there's going to be a bottleneck. Theta dot is going to be 0 for theta equals to pi by 2. And what's going to happen is that the trajectory is going to get, whatever it's doing, it's going to get stuck at this particular point, because theta dot is now 0. So that's going to be an infinite period at mu equals to 1. And this is the bottleneck. So at mu equals to 1, we have it's an infinite period bifurcation, because the period has suddenly become infinite. Though the amplitude remains the same, amplitude remains order 1, but the period becomes infinite. And what happens for mu if mu is less than 1? Theta dot equals to mu minus sine theta. So then of course there exists theta for which this guy is 0. So I have, what happens is that this particular fixed point splits into 2, because now I have this guy and this guy. And what's happening in the r direction is that the trajectory will go, of course, over here, and from outside the trajectories are getting also attracted. But I have essentially two directions where I have these invariant rays. So for mu less than 1, there are invariant rays defined by sine theta equals to mu, where essentially nothing is going to happen. The trajectory, if it is stuck here in theta direction, when sine theta equals to mu, it can only go here. and get here. It can only go here, from here it can get here. So on these rays nothing happens in the theta direction because theta dot will become 0. Only thing is this thing. So the over here I get a fixed point, stable fixed point, but at the other value of theta I have a saddle where this is repelling in the theta direction but it's attracting in the r direction. So this is a saddle. And this bifurcation is called as the infinite period bifurcation because upon changing the parameter my simple flow on the dynamical system became a bottleneck infinite period. So one can summarize the kind of bifurcations we have seen through this particular chart, that qualitatively what's happening. So I have the bifurcation type. And I can write the amplitude, I can write the period. So I had the Hawk bifurcation. Of course I had the Hopper bifurcation also, supercritical, subcritical. What happened over here? The amplitude increased very slowly. And the period was, we didn't talk about the period was same. Nothing happened in the theta direction to make a comment. Subcritical was a dangerous bifurcation, remember? The fixed point loses its stability and the trajectory immediately jumps to a attractor of order 1. And the period was also of order 1. Then we had the saddle node bifurcation of cycles. Over here, 2 cycles coalesced or were created immediately, and the amplitude was again order 1. Remember, this was the over here at this point immediately the bifurcation was called, and this is roughly an order 1 in R. So the amplitude of the cycle was order 1 and the period was also order 1. And then we have the infinite period bifurcation. Where the amplitude of the oscillation was order 1, but the period increased. You can show this. This increased very slowly and this goes to infinity. And that was my infinite period bifurcation. So these bifurcations are very important because the focus of the next lecture is going to be the Lorentz system, which is a chaotic system in which what happens is that suddenly the system, like over here we had the system jumping to a stable attractor. Over there the system is going to go under a bifurcation, it will lose limit cycles and the system is going to hit an unstable attractor or a strange attractor, which is going to be a chaotic fractal kind of a structure. So we are going to study that in the subsequent classes, and that's why these bifurcations are important. I mean, the field of dynamical systems is so rich that we started from simple fixed points to bifurcation of fixed points, and then some very interesting things are already happening in 2 dimensions. And if you go 3 dimensions beyond, they are not only limit cycles and fixed points, there are these attractors which have a fractal dimension, and the trajectory settles on those attractors through as we go through these bifurcations. So we are going to look at that. So also from the next lecture we are actually going to start our discussions on flows in ODE systems. We already saw chaos in the logistic map. So all those concepts of invariant density, Lyapunov exponents, sensitivity to initial conditions are very valid for flows, but we are going to see a very canonical example of a chaotic system, the Lorentz system of equations. So thank you.